Hi class, welcome to our lecture on assumptions, and this is our introduction to assumptions. We're going to cover what are they. We'll talk a little bit more about univariate normality, which is the first assumption we'll be working with. Talk about level of measurement, independence of observations, and homogeneity of variance, which are some of the first basic assumptions that we run into as we start running statistical techniques. And then we'll just introduce the model level assumptions because we'll get into those more in depth later in the term. Assumptions are exactly how they sound. What we believe to be true about the variables or model, which then dictates the decisions we make about analyses and the conclusions. So we're going to learn about several types of assumptions that are related to the techniques we're running. Some assumptions are only specific to the variable, like if it's a categorical or continuous variable, or a specific relationship being examined, like a categorical predictor with a continuous outcome. And some assumptions are about the model itself, like the normality of residuals or multicollinearity. Additionally, you'll find a range of opinions about the relevance of assumptions. I fall somewhere in the middle, where we're still going to check the assumptions, but I'm also going to have you guys run parametric techniques to get that skill base down, because it'll be easier to do non-parametric once you learn the parametric technique. So we'll learn more about each assumption as we get to its specific technique that they're relevant for. And we're going to introduce several assumptions now. The first assumption that we will work with is called univariate normality. So univariate means one variable, and we're looking at, for one continuous variable, is the distribution of it, the scores on that variable, are they distributed normally, that nice normal curve. We would like our univariate distributions to be normal. They don't necessarily have to be, but it's better if they are as normal as possible. And there's different ways to detect if a variable is violating univariate normality. We can look at histograms, we can look at skewness and kurtosis, and we can do certain tests in our statistical software called normality tests. When we're looking at a histogram, we're doing a visual inspection, and we can easily identify outliers. Outlier is an extreme score that is much either higher or lower than the rest of the scores in that distribution, and it has an impact on the distribution of the variable and certain statistical techniques as well. So that would indicate a violation of univariate normality. Another way to look at normality of a variable is with skewness and kurtosis, and these are estimates of the shape of that distribution. When you have most of the scores kind of piled up on the lower end of the scale with this long tail going out on the positive direction of the number line, that's considered a positive skew to the distribution, a violation of univariate normality. The other one is when you have a large pileup of scores happening in the upper end of the range of scores possible, and you got this long tail going out in the negative direction on a number line, and that's a negative skew. Now kurtosis might have scores all along the way and might have its bulk of distribution in the middle, but when it's really peaky in the middle and doesn't have many scores in the tails, that's considered a positive kurtosis. Whereas a negative kurtosis is going to have these fat tails. They don't stream out and get smaller very well. It's more of a flat distribution because it's got these fat tails, whereas your normal distribution just follows that normal curve well. So you'll look at the characteristics of a distribution of a continuous variable and look at both the skewness and the kurtosis, as well as looking at the histogram to give your perspective, your results on what you have determined is the distribution of that variable. We also have a couple of normality tests that we'll be working with: the Kolmogorov-Smirnov test and the Shapiro-Wilks test. Typically we're using Shapiro-Wilks. And in the notes section of the PowerPoint, I also left a website link that does pretty good at talking about skewness and kurtosis itself. Some other basic assumptions that I wanted to introduce you to that have relevance across a lot of our techniques is the level of measurement. Depending on the technique we're using, it might require a categorical variable or a continuous variable. So our categorical variables are the nominal and ordinal types. When we name things like male and female, or racial groups would be nominal. Ordinal is going to be those ordered variables like first, second, third place, or highest education earned would be somewhat of an ordinal scale, where more means a higher rank, that kind of thing. Whereas your interval and ratio are considered continuous variables normally. And that's when you have proportionate intervals between the variables. And with ratio type of measurement, it can also have an absolute zero. In other words, zero has meaningfulness. There, zero has a meaning. Whereas with interval scale, I could assign something on a 0 to 4 scale, and I could just as easily assign it to a 1 to 5 scale. It wouldn't change any meaning there. But if I all of a sudden decided that age is going to be 5 years old and 0, that didn't make any sense anymore. That, no, a 5-year-old's a 5-year-old and a 0 is a 0, right? So if a measurement has a meaningfulness at 0, it's more likely a ratio. Regardless, both interval and ratio are considered continuous variables most of the time. Our next one is called independence of observations. So this is another basic assumption where we're expecting, when we're conducting a study, that all of the participants are independent of each other. If one walks in to do our test or our survey, we're not expecting that they already heard about what was going to be on the survey from someone else, or they already saw someone else do the exercise that we're running as an experiment. In any situation where the observations or measurements are collected like in a group setting, or where participants are involved in some sort of interaction, this could introduce a non-independent situation for the data, and then would be a violation of independence. The examples that our book brings up are when students are working in a group, maybe when we're looking at TV viewing habits in a family, or you have children all in one with one teacher or with one school, that if you're looking at differences between individuals and they're all grouped together, that's a violation of independence of observations. Bivariate linearity refers to the relationship, the linear relationship between two continuous variables. So you're going to see this one more often in your regressions, correlations, when we're looking at relationships between variables. If we're saying that one predicts the other, then we have the assumption that they are related linearly. So that is something that we can check both visually with a scatter plot, and also we can test it with a correlation test. Another one I wanted to introduce you to was homogeneity of variance. And because some of our parametric techniques, especially those that evaluate outcome differences between groups, they make the assumption that the samples that were our sample from the population is drawn from a population that has equal variation on that outcome. For example, if we're looking at kids' writing ability, we're expecting that drawing from the population that there's this equal distribution of writing ability across all kids, right? But when we look in the data and we see that public school kids have this wide distribution of their writing proficiency, whereas private school kids have a much shorter, skinnier distribution, that would be a violation of homogeneity of variance. Same here, if we had 4 groups representing educational level, high school, associates, bachelor's, and grad school, and we're saying on the outcome of work hours, how much are there differences in how many work hours someone works a week on average between those groups, and then the spread of work hours, we're expecting those to be equivalent spreads. So that variance is a measure of spread of the distribution. So these obviously are examples of a violation of the homogeneity of variance. Something that was meeting that assumption would have similar widths on these blocks. And there are also tests that we use to test homogeneity of variance, which we'll get into more when we do our work with comparisons between groups, like our t-tests and our ANOVAs. And then finally, I just wanted to throw these words out at you, let you start getting used to them, because we'll work with them more when we get into checking assumptions of residuals and models in our regression labs. But a few of them are multicollinearity and singularity. So multicollinearity is when the predictors in a model are too highly correlated, and that can introduce problems in the estimation of the model and the interpretation of what's going on. Singularity is when the scores in a subscale and the total of that subscale are included in the same regression. That would be a problem because we're kind of counting it twice. So each item needs to only be represented once singularly. Outliers, as we spoke of, are very high or low scores that differ substantially from the main trend of the data, and those are important in our model level assumptions as well. And then we have these assumptions about the residuals: normality, linearity, and homoscedasticity, and independence of the residuals. Now, what are residuals? Well, we'll get into residuals more in depth during our regression topics, but in a nutshell, the residual is this difference between what we predicted a score to be and what it actually was. So our prediction line, that dark black line, says that if someone had a 4 on this X variable, we would expect them to have like a 4.5-ish on the Y, on the dependent variable, on whatever that is. And that's what we would predict that anyone getting a 4 to end up with as that outcome score. But what they ended up getting was like a 5 right there. That difference between the 5 and the 4.5 is the residual. Sometimes you'll also hear it called the error. We had what we expected and what we didn't expect. That was the error or residual for that model. So, don't worry, we'll go into it more when we get to regressions. Little recap. Of course, all parametric tests assume certain characteristics about the data. and violation of these assumptions changes the conclusion of the research and impacts the interpretation of results. So assumptions vary depending on the type of analysis being conducted. When we're conducting analyses that looks at relationships between variables, some of the basics are we're expecting those variables to be normally distributed, and we're expecting that the outcome and predictor are related, and that's called bivariate linearity. Assumptions that are specific to our comparisons between groups types of analyses are that the groups that are being compared have similar variation on that outcome. We also need to have enough sample size and sufficient numbers in each group. And to run the test, we only need 5 in each group. But to actually detect differences and detect meaningful effects, you're looking at more like 30 in each group. And then assumptions related to statistical models, we'll be getting into more later, are multiclinearity and singularity, and normality, linearity, and homoscedasticity of residuals. And sometimes we find that there are too many violated assumptions to use the test that we had intended to conduct. That's okay. That's when we would move to an alternative approach called non-parametric statistics. You're going to find out more information about that when we get to that week, and they are in chapter 16 in your book. In fact, if you look at the notes in this PowerPoint, I put the page numbers on from your Pallant book for where she discusses these different types of assumptions. So be sure to look through the notes, get more familiar with these different types of assumptions so that we can delve into them when we start running more analyses. So thank you so much for hanging out with me for this assumptions introduction, and I look forward to seeing you in class.